Now it is my great pleasure to introduce Professor Lorenzo Faraone. Dr. Lorenzo Faraone is a member of the Order of Australia and a fellow of the Institute of Electrical and Electronic Engineers, the Australian Academy of Science, and the Australian Academy of Technological Science and Engineering. He has published more than 300 international journal papers on his research work and supervised more than 40 PhD students. He is currently the head of the Microelectronics Research Group at the University of Western Australia and the director of WA node of the Australian National Fabrication Facility. Prior to joining UWA in 1987, he worked primarily in the area of silicon CMOS-based microelectronics and non-volatile memory technology with RCA Labs in Princeton, New Jersey, USA. Since joining UWA, he has worked on compound semiconductor materials and devices, including aluminum gallium nitride, HEMTs, mercury cadmium telluride-based infrared sensor technology, and MBE growth, as well as optical MEMS technologies for infrared spectroscopy and imaging applications. His research activities also include mobility spectrum analysis techniques for magnetotransfer studies, which allow the transport properties and mobility distributions of individual carriers in multi-layer or multi-carrier semiconductor systems to be determined. On behalf of all the members of RIERS, I welcome you, sir, to this webinar. And I also welcome all the invited guests and participants to this webinar. Our humble request to all the participants, all are requested to keep their microphones muted till the end of the webinar. After the talk, time will be given for interaction with the speaker. Also, all of you please take care not to share your screen in between. Link for generating e-certificates and providing feedback will be given at the end of the webinar. Now I kindly request Professor Lorenzo Faraone to begin the presentation.
Thank you very much for inviting me to give this presentation, and thank you for the very kind introduction. I'm very happy to give this presentation and share it with, I get the impression that most of the people, or a lot of the people, will be from India, and it's a place that I have visited many times over the years. So I'm going to talk tonight about optoelectronic technologies for high-performance infrared sensing and imaging arrays, which is a very, very broad and deep topic, but I'm going to try and give you a bit of an overview, a little bit of a tutorial, a little bit of a background in terms of the semiconductor technologies that are required to for high-performance infrared imaging and sensing arrays. So my name is up there as a presenter of this webinar, but of course the et al. In the title also includes my co-workers, and the people shown in this photograph are the essentially the infrared sensor group. There's also a MEMS group which is separate from this, but I'm the head of the whole activity. So I have to thank my co-workers who really do the actual work. I'm just the head of the group. So okay, so I'm going to be giving you a bit of a background in terms of infrared basics for those of you who are not that familiar with the infrared part of the electromagnetic spectrum, and what's required in terms of the semiconductors for fabricating infrared sensor arrays or imaging arrays. And that essentially comes down to the next section, which will be on a little bit on MBE growth and the characterization, modeling, and simulation capabilities required to make that a success. And then we'll look at some infrared photodetector and imaging array technology. As I said, this is a very complex area, and so I'll basically just have to cover in some of the areas very briefly and at an overview, and I will use some sort of examples from you'll see photographs, images shown around the place. These are all images from our lab, and I'll describe a little bit about what they are, etc., as we go through it. So I will use examples from my lab, although I'll try not to make this sound like an advertisement for our research group or from our research labs or from our research activities, but I will use examples just simply to demonstrate what we're talking about. So going back to first year physics, Planck's black body radiation law. And so if you look at the black body radiation, which can pretty much approximates the thermal emission from a body at a particular temperature. And if you look at this particular curve here, 300 Kelvin, which is basically represents the temperature at which, you know, for a human body or from the Earth's surface, it's somewhere around about 300 Kelvin, plus or minus 10 or 20 or 30 degrees. So it's somewhere around 300 Kelvin. And you'll notice that the peak radiation emitted by a body at 300 Kelvin is at around about 10 microns in wavelength. So just keep that number in mind. Around 10 microns is the peak radiation for something at room temperature or human body temperature, etc. And then you'll notice that at 500 Kelvin, the peak is closer to in the sort of more in the 3 to 5 micron band. And then as the temperature increases, the peak emission moves to shorter and shorter wavelengths. Whereas in the shortwave infrared, there's not much thermal emission. And in the shortwave infrared, you're basically looking at reflected shortwave infrared. Now, the reason for those designations is because if you look at the designation long wave, midwave, and shortwave, they correspond to atmospheric transmission windows. So if you look at the infrared transmission through the atmosphere as a function of wavelength, there is a window in the long wave infrared where there is high transmission. There's a window in the midwave infrared and a window in the shortwave infrared. And so within these atmospheric windows, as they're called, it means that you can visualize something over a long distance through the Earth's atmosphere. And notice that there's a region in here where the atmosphere is opaque because of high absorption due to water vapor and other constituents in the atmosphere. So these designations come from mainly defense applications for thermal imaging or infrared imaging applications over long distances through the atmosphere. That's why there are those designations. And if you look at the applications of infrared imaging, the obvious ones are for night vision in surveillance applications. So this shows you a thermal image, an image in the visible and what you see in the thermal, and you can see that there's something there that you cannot see in the visible. The other advantage of infrared is in terms of fog and mist, infrared transmits much better, especially in the shortwave through fog and mist. And so you can basically visualize things that is very difficult to visualize through a visible camera compared to a shortwave infrared camera. There are the obvious ones. Once again, this is another thermal image. There are remote sensing applications from satellites, where this shows you actual bushfires occurring in Australia last summer. The coastline is along here, it's a bit hard to see, but you can see for bushfire detection, also many applications in astronomy, and of course the recent James Webb Telescope is using infrared imaging arrays for its magnificent images that we're seeing. There's also a whole range of applications, especially in spectroscopy, infrared spectroscopy in agriculture, for precision agriculture, in medical diagnostics, and also in in measuring faults in electrical equipment, etc. So there's a huge range of applications for infrared imaging in different wavelength bands for different reasons. Now, if you look at the performance of an infrared detector, the one parameter that sort of defines its performance is called the detectivity, or D star. And essentially what D star is, it's a measure of the signal to noise ratio. In the end, imaging is all about extracting the signal from the noise. And a lot of electrical engineering, of course, is about detecting signals, measuring signals, interpreting signals, but all signals have some noise associated with it. And so a high signal to noise ratio is something that you always aim for. So if you look at this equation for D star, on the top you have, this is the area of the device, this is the temperature, Boltzmann's constant, and this is the dynamic resistance. Let's not worry too much about what that means. The important parameters here is, if you look at it, is you have this thing called the responsivity. This is basically measures how much photocurrent I get out of my detector for a given amount of input optical power. So I want high responsivity because this is my signal. And then if you look at what's in the denominator, you'll see this I dark. This is the dark current. So this is the current that flows through the detector without any light or without any photons impinging on it. And this dark current is what generates the noise in the detector. So this is basically the signal, and this is what generates the noise. So detector technology is all about increasing the responsivity, the signal, and reducing the noise, which is the dark current. And if you look at the responsivity, the signal, what you find is at a first order, it's proportional to this parameter alpha, which is the absorption coefficient of the semiconductor material in terms of how efficiently it absorbs the infrared photons. So obviously you want high absorption coefficient. And it's also got this parameter mu tau, which is the mobility times the lifetime square root of. So in order to get a high responsivity, you want a high mobility and a long lifetime. And what this means is that if I have a good absorption coefficient, it means that I'm absorbing photons and generating electron-hole pairs. What the high mobility and long lifetime gives you is it means that I can collect those electron-hole pairs, which gives me my photocurrent in my responsivity. Okay, so first of all, I have to absorb the photons, and then I have to collect the photons. And if I've got high absorption and efficient collection, I end up with a high quantum efficiency. And that's what it's all about in terms of maximizing the signal. Okay, so, and the dark current, as I said, the noise that's generated within the detector is very much related to the dark current, which relates to a whole bunch of parameters, which is far too complicated for me to get into now. But it does relate very much to the generation recombination rate, which means that the energy band gap of the semiconductor affects the dark current. And so in a very simplistic point of view, you can say that if I look at different wavelength bands, and this pretty much represents the shortwave infrared, the midwave infrared, and in this case, long wave infrared, or pretty much all bands. Basically what happens is that from a device technology point of view, the technology gets more and more difficult the longer and longer the wavelength I'm trying to detect. And the reason for that is because the energy band gap gets narrower and narrower as I go to longer wavelengths. And so the generation recombination rate increases, and so the noise increases, which means that in order to reduce that noise, I usually have to cool detectors in the long wave infrared to around 80 Kelvin, in the mid wave infrared to around 150 Kelvin, and in the short wave infrared, they can operate at room temperatures. So the technology gets more difficult as I go from short wave to mid wave to long wave, and the operating temperature, in order to get a decent signal to noise ratio, I have to cool further and further as I go to longer and longer wavelengths. Now, what this table shows you is pretty much the dominant semiconductor technologies in those different wavelength bands for various reasons. In the end, remember that you have to absorb photons. And so in order to absorb photons, you really want a bulk semiconductor. And so indium gallium arsenide in the shortwave infrared up to about 1.7 microns is a magnificent infrared detector material, up to 1.7 microns. Indium antimonide is an excellent infrared detector material, but it has a fixed cutoff wavelength at 5 microns, so it cannot operate in other wavelength bands. So indium gallium arsenide and indium antimonide are basically fixed in the shortwave infrared and the midwave infrared. And then over here, there's this other material called mercury cadmium telluride. And in this case, this material is very unique because I can actually change the energy band gap by changing the alloy composition from mercury telluride all the way to cadmium telluride. And I can actually fabricate from mercury cadmium telluride detectors in the shortwave infrared, the midwave infrared, or the longwave infrared, and in fact into the very long wave infrared. So it has a tunable energy band gap, and throughout that, excuse me, change in lattice, in alloy composition, the lattice does not change, and so I can grow heterostructures and all sorts of multicolor detector structures. Now, if I look at these three dominant technologies in these three wavelength bands, they have very high quantum efficiency. They've got pretty low dark current, although certainly when I show 3 arrows here for mercad telluride, I mean if mercad telluride was in the midwave or the shortwave infrared, it would outperform indium gallium arsenide and indium antimonide. And one big advantage of mercury cadmium telluride also is that in avalanche mode, so if you're trying to make an avalanche detector for single photon avalanche detectors or for linear mode avalanche detectors for LiDAR applications in the infrared or stuff like that, then mercury cadmium telluride has a very big advantage because it has a very low excess noise number, excess noise figure, which means that it basically does not add hardly any noise when it's avalanching compared to the other technologies. However, the one killer for mercury cadmium telluride is the fact that there is no large area high quality substrate available to grow mercury cadmium telluride. And so it will always be, at this stage, a high cost technology, but it is by far the highest performing technology. So if you're looking at astronomy applications, if you're looking at high performance defense applications, then mercury cadmium telluride is basically the infrared material of choice. So if you look at this graph here shows you the energy band gap versus the lattice constant. Sorry, the label's missing down here. The important thing, which I've already noted, is that mercury cadmium telluride, which is this blue line, from mercury telluride to cadmium telluride, I can change the energy band gap from just over 1.5 electron volts all the way down to a semi-metal, which has a negative band gap, which means I can span the shortwave infrared, the midwave infrared, and the longwave infrared, which all sit around here somewhere, with a single material system, just by changing the ratio of mercury to cadmium in the alloy. And the important thing is, this is almost vertical line, which means that the lattice constant virtually does not change. So it doesn't introduce any stress in the semiconductor crystal or generate defects if I vary the composition within the device structure. And so if you look at the wavelength range for those detectors that I mentioned, these are other impurity band detectors, which are not really competitive from an imaging point of view. So here's indium antimonide, which cuts off at around 5.3 microns or so. Indium gallium arsenide at about 1.7. But basically, mercad telluride can cover all of those wavelength bands. And so this sort of says why mercury cadmium telluride is essentially the material of choice for ultra high performance. You can see by changing the cadmium composition in the alloy, I can tune the cutoff wavelength anywhere from the shortwave infrared into the midwave infrared out into the longwave infrared. If I look at the absorption coefficient, notice below cutoff, I have an absorption coefficient of around about 10 to the 4. What that means, 10 to the 4 inverse centimeters translates to it means that I only need about a micron of material to absorb 50% of the radiation. So if I have a layer of mercury cadmium telluride that's maybe 4 or 5 microns thick, then I can basically absorb 100% of the radiation. It's all gone. It's all been absorbed in a very thin layer. And then if you look at the electron mobility, and mercury cadmium telluride has a very high carrier mobility. We're talking about, for electrons, around about 10 to the 5 centimeters squared per volt second. And if you look at the lifetime, high quality material typically is around here, with a lifetime around about a microseconds or so. And so if you remember the equation for D star, we have the absorption coefficient, which in this case is a high absorption coefficient, the electron mobility, and the lifetime. And so if you look at this mobility and you look at this lifetime, this mu and this tau, and calculate the diffusion length for those two numbers, you get diffusion length of the order of 10 to 100 microns. And what that means is that when I generate electron hole pairs, those minority carriers, which end up being the photocurrent in the detector, they can travel 10 to 100 microns before they will recombine. So this high absorption coefficient means I absorb all the photons and generate electron hole pairs, and this high mobility combined with a long lifetime gives me long diffusion length, which means I can collect those electron hole pairs very efficiently, which gives me the photocurrent in the external circuit, which of course is my signal. Okay. Now, the thing about infrared technology is that because of its very nature, and also because it is a very defense-oriented technology, a lot of things tend to be restricted. A lot of information tends to be difficult to gather, and people just basically don't talk too much about these things. So in our particular case, we have what's unusual for a university is a vertically integrated capability where we can undertake infrared sensor design and modeling. We have a very sophisticated device simulation package for mercury cadmium telluride, infrared sensor design. We can grow the material in our MBE lab. We can take it up into our clean room and fabricate infrared imaging arrays, and then package them using a flip chip bonder, which basically bonds the two-dimensional infrared imaging array onto a two-dimensional CMOS readout integrated circuit. And then we can package it out and test it on our focal plane array test system here. So yeah, I'm not going to spend too much time in terms of the details of device modeling and simulation, but it does require some fairly good modeling capabilities to design the detectors, because you can vary the doping in the material as a function of position as you grow the layer, and you can vary the composition going back to the ratio of the mercury to cadmium. And you do that in order to grow a wide bandgap layer at the back of the substrate, at the back of the epitaxial layer, as well as at the surface, in order to minimize surface recombination, for example, just to give you one example. MBE growth, this is a whole technology in itself, and requires, well, obviously an MBE system that's designed in this particular case specifically for mercury cadmium telluride. It's a Rebair 32P, a 3-inch system, where we grow, as you can see, mirror-like surface layers of mercury cadmium telluride on cadmium zinc telluride, which is the substrate that's lattice matched to the mercury cadmium telluride. And we have in situ read as well as other diagnostic tools on the MBE machine. And then the layers are typically characterized primarily for defect densities, because in the end you're trying to make an imaging array. So typically for imaging arrays, we would grow on a 15 by 15 millimeter or 20 by 20 millimeter substrate. And for an imaging array, of course, you need to reduce the defect density in the material in order to improve the yield, and also in order to improve the uniformity of the detectors across the array. Yeah, and so the typical numbers that you need to get to is what this is etch pit density. You need to get etch pit densities down in the low 10 to the 4 per centimeter squared. You need to be down in this quadrant down here before you can really fabricate infrared imaging arrays. If you're down in this quadrant down here in the low 10 to the 4 per centimeter squared, then there is a likelihood that you will fabricate arrays with a yield, detector yield that's above 99%, which is what you really want for an imaging array. If you're up at this end at higher numbers, then your pixel yield in your imaging array is going to degrade very rapidly. So going back to this table again, and just to emphasize the fact that the big disadvantage of mercury cadmium telluride and why it is such a restricted technology, in the sense that it's not readily available, besides its defense applications and space applications. The other reason is simply because it is a high cost technology, because there is no substrate on which to grow the mercury cadmium telluride that is lattice matched to the semiconductor. And if you're going to grow high quality material, excuse me, which is what's required for a semiconductor device, then you really want it to be lattice matched. So people have been trying to grow mercury cadmium telluride on other substrates such as silicon, gallium arsenide, germanium, gallium antimonide, etc. But notice that all these substrates, which are available in large area at low cost, don't match the lattice of mercury cadmium telluride. So that's a major technological constraint for this technology. So I won't go into detail here, but you'll see if you try to grow mercury cadmium telluride on silicon or on gallium arsenide, you end up with defect densities, etch pit densities, in the sort of low to mid 10 to the 6 per centimeter squared. Whereas if you grow on the lattice matched cadmium zinc telluride, then you're about 2 orders of magnitude lower than that. So at this stage, there's still no alternative, certainly for high performance imaging arrays, except to grow on cadmium zinc telluride. We have worked on, and there's other people working on such technologies, on when you're growing mercury cadmium telluride or any semiconductor on a lattice mismatch substrate. We've used MBE in our MBE system, what we call dislocation filtering layers, which basically are very thin layers which have alternating layers of, in our case, cad telluride, cad zinc telluride, cad telluride, etc., multiple layers alternating compressive and tensile stress. And the idea of this is that using this structure in each of these dislocation filtering layers, the idea is that if you get a defect that's propagating from the substrate because of lattice stress from the cad telluride gallium antimonide interface, that defect structure, which is a threading dislocation, can either terminate or perhaps be deflected by these dislocation filtering layers and not reach the top layer, because of course it is the top semiconductor layer where you fabricate your device, and this is the crucial layer from a device performance point of view, not down here. And we have shown, and other people have done this with in 3.5 semiconductors on lattice mismatch substrates, but this is we're the first ones to have done it on 2.6 semiconductors for infrared imaging devices. And you can see that we're able to reduce the etch bit density by about 2 orders of magnitude by using these dislocation filtering layers. Still not good enough. We're only just getting around 10 to the 5 per centimeter squared. So there's still some work to be done there. And you can see evidence here in this electron micrograph of threading dislocations, threading through from the substrate, and when they hit the dislocation filtering layer, they terminate. And similarly, there's another one here that terminates in the filtering layer. You can see the alternating layers of compressive, tensile, stressed layers within that dislocation filtering layer. So as I said, this is still sort of unfinished. So there's some work here from other people for gallium arsenide on growth of gallium arsenide on silicon, and this is our work for cadmium telluride on gallium antimonide. And you can see very similar trends, very similar behavior. But 10 to the 5 is still not really good enough. So then, once you've perfected or have reasonable quality, high quality mercad telluride, then you have to fabricate the imaging array in the clean room facility. I won't go into details about that, except just to simply show you the test chip down here, or not the test chip. This is actually a 640 by 512 pixel array. 640 by 512 is quite typical for infrared imaging applications used for night vision, missile guidance, missile approach warning systems, surveillance from drones, etc., etc. It's a very common format for an array. 640 by 512 gives you good enough imaging quality for most defense applications, and also even for satellite-based applications for remote sensing, etc., and Earth observation. So we fabricate the array in here, and we have a bunch of test chips and other things for testing the detector's performance. And once we're happy that things look okay, we can actually cut out the array and flip chip bond it to the silicon CMOS. I won't go into details about this typical detector structure that we use, except to note that if you look at the typical device structure here, this is the substrate down here. We usually grow a wider band gap semiconductor, X equal 0.4, and then X equal 0.3. So the X equal 0.3 is what corresponds to the mid-wave absorber. This is a wider band gap, and so the infrared, so it's transparent to the infrared photons which come in from the back. The substrate is transparent. This X equal 0.4 layer is transparent, so the photons are absorbed in this purple layer of 0.3 material. And then we grow an X equal 0.4 layer at the surface, followed by a cadmium telluride cap. So that whole layer of 0.3, 0.4, 0.3, 0.4, and then essentially 1 for the cad telluride, all of those 5 layers are grown, or 4 layers, and plus there's graded layers in between, are grown in a single growth run within the MBE machine. So you see it's a little bit more complicated than just making a diode. Although in the end, that's really all a photovoltaic detector is, right? It's just simply a diode, similar to a solar cell. So once the array is fabricated, you then need to form what I called indium bumps. So on each of the detectors on your 600, so this has 640 by 512 detectors on there. So it has over nearly 400,000, nearly 500,000 detectors in that area there. And that area is around about a centimeter by a centimeter. You then have to form indium bumps, which are simply indium balls on the top of every detector, because that's what's going to form the electrical contact to the silicon CMOS readout circuit. And so here, this shows you cut the detector out here, and then you have to, using a dicing machine, and then you have to flip chip bond it, basically face to face on a silicon CMOS chip, which sits underneath, and the detector array sits on top. They're facing each other, and you have to make 640 by 512 electrical contacts between the indium bumps on the detector array to the indium bumps on the readout circuit. And then you can wire bond it to the outside package, and you end up with a readout circuit a focal plane array flip chip bonded onto the readout circuit. And then, of course, there's a whole array testing system, which basically allows you to measure the uniformity and yield and performance of the individual pixels in an imaging array, as shown here, for example. So all of this takes a long time. So we've been in this business for well over 20, 30 years, starting back in the 1990s. Excuse me. And we have fabricated a number of different technologies along the way, and we're currently finalizing the 640 by 512 mid-wave detector array, although we have successfully fabricated a 320 by 256 array, which we'll show you here. So this is a movie of our 320 by 256 mid-wave infrared imaging array. You can see when he puts his hands on his shirt and then he takes it off, you can still see the handprint on the shirt, as well as you can see through the pocket that he has his identity card inside the pocket. Okay, so that's pretty much what an infrared imaging array technology looks like, from all the way from growth to fabrication to packaging and testing, etc. And there are some other challenges still around for specific applications, and I'll just describe a couple of them to you. One of them is a challenge to produce ultra-high quantum efficiency detectors at around about 2 microns. And the reason for this is, and when I say ultra-high quantum efficiency, I mean external quantum efficiency is greater than 99%. And the reason you want these ultra-high quantum efficiencies at a wavelength of 2 microns is because for two specific applications, gravity wave detection and optical communications, because 2 microns happens to be a very good transmission window through the atmosphere. There's very little, it basically represents a minimum in terms of scattering and absorption. So you can see further at 2 microns than you can at any other wavelength, and which has obvious applications for optical communications, for example, satellite to ground, etc. And also it means that it has been looked at as the wavelength of operation for the next generation gravity wave detectors in their interferometer, because they want to maximize their signal in terms of the laser used in the interferometer. The other advantage at 2 microns is that there are high power lasers available at 2 microns, holmium doped fiber lasers. So this is an interesting challenge for the infrared detector community, because achieving quantum efficiencies greater than 99% is going to be a real challenge. And from our modeling work, which we have undertaken, it looks like it is possible to achieve, but it can only be achieved by mercury cadmium telluride. There is no other semiconductor technology that can get close to 99% quantum efficiency at 2 microns. For example, indium gallium arsenide below 1.7 microns, for example, at 1.55 microns, the other telecommunications wavelength, you can achieve close to 99% quantum efficiency. But at 2 microns, the performance of indium gallium arsenide falls off very rapidly beyond 1.7 microns, and you'll never get 99% quantum efficiency. So we're sort of looking at this as a challenge for the future. And the other one is developing avalanche photodiode detectors also at 2 microns for long-range remote sensing and LiDAR applications. So there's a lot of interest in developing 2-micron avalanche photodiodes, once again, which can only be done with mercury cadmium telluride for long-range detection of drones and things like that, for LiDAR type single photon avalanche detectors or operating in linear mode, etc. And this just shows you some preliminary results that from some of our devices which are not quite linear yet, but we'll get there. So you can see here you can get a gain. This is a 2.2 micron cutoff, so this is at around about 2 micron wavelength. You can see that you can get a gain of around about 100 when you apply about 8 volts in reverse bias. So they're the 2 challenges that we've set ourselves for in terms of devices. And the real big challenge, though, for infrared technology is cost. And the main challenge, certainly for mercury cadmium telluride, is the cost of the substrates and the quality of the substrates and the area, the size of the substrates, because it means that you can't fabricate devices like you can fabricate CMOS chips on large area wafers, where you produce hundreds of chips on one wafer, and then you dice them up once you've finished. So until that kind of technology becomes established, unfortunately, high performance infrared imaging arrays are always going to be high cost, which is unfortunate because they do have a lot of applications, certainly in medical applications, in precision agriculture, remote sensing, mineral exploration, for example. So in terms of the requirements, you really want to get us into a situation where the performance, the resolution, and the format is at least improved by a factor of 10, increased by a factor of 10. If you look at infrared arrays compared to CMOS imaging arrays, you really want to get the yield, operability, high yield and operability to reduce the cost by at least a factor of 10. And the only way that's ever going to happen is if you can end up with a sort of silicon CMOS-like technology, which is based on large area, high quality substrates that you can fabricate imaging arrays in a similar way to the way you fabricate memory chips or microprocessors or whatever, or CMOS imaging chips like the ones that are in your mobile phone, etc. Until that happens, unfortunately, infrared imaging capability is always going to be a relatively high cost undertaking. Now, of course, people say, yeah, but I can go out and buy a really cheap long wave infrared imaging, thermal imaging camera. Yes, you can. And it'll be based on a microbolometer structure, etc., etc. And that's fine for night vision, using in surveillance applications, out looking over a car park, etc. But their response time is very long, typically orders of magnitude slower than a photon detector, which is what I've been talking about. So I've been talking about high performance infrared imaging arrays, not low performance, which is what microbolometers are. So if you want to detect anything that's moving rapidly, like a missile, or if you are moving rapidly, then you really need photon detectors, not bolometric detectors, which are much slower. So that's the challenge that the industry faces, and probably best if I stop there and take questions or whatever. Thank you very much.